Hi there, I'm Maxwell Doolin. I also go by Strikeout. Earlier today, we did a recording of a talk on the recent Sushiswap hack. However, we had some technical difficulties, and so we decided to re-record it. So I'm just gonna get into it then. So on April 8th, the prominent security researcher Trust tweeted this. It was, I just white hacked Sifu for 100 ETH. I would like to return it. Please contact me in the DMs. And this started a whole chain of actions. If you look down here, you can now see this is insane. Me bots have deployed contracts and copied the attack before I could save everything. That was pretty wild. And it turned out that there was actually a lot of funds that were at risk and in a contract that was only 4 days old. Now, PeckShield picked up on this and said that there's a copycat, had some links to some addresses, and they said that there were a lot of funds that were directly at risk. Particularly, Sifu had about $3.3 million worth of ETH stolen. Now, this is a pretty big deal because it's Sushiswap, right? You know, it's a pretty popular automated market maker. Because of this, SlowMist decided to do some coverage on it. And this was when I really started getting interested. It's like, how does this actually work? According to SlowMist, it ended up being, or to PeckShield in a different post they had, ended up being a approval related bug. You can see here that please revoke approvals ASAP. And SlowMist then goes through the entry points, see how an attacker can hit this, which is where I got most of my information prior to launching an attack. So in this presentation, or this video, whatever you want to call it, we're going to go through the exploitation of this bug. We're going to go through the bug discovery, but we're not just going to exploit for one user. We're going to create a script that goes through the discovery of the vulnerable users and pwns every single user that was vulnerable to this attack. And we're going to do some of this live, which I think is pretty fun. So if we go back to the SlowMist report, we see that the root cause is that the process route does not perform any checks on user-provided route parameter. This allows the attacker to exploit this issue by constructing a malicious route parameter that causes the contract to read a pool created by the attacker. We see that process route is the external call you can make, and they are hitting the Uniswap v3 functionality. Within there, the value last called pool is actually what's hit. Important thing to know about Uniswap v3 is unlike Uniswap v2, where you approved the contract to spend funds on your behalf, you actually don't do that anymore. Instead, there is a callback function. And this callback function uses the contract's approval in order to transfer the funds to it. And that is what this is talking about. So from reading this, we know that swap uni v3 is the function we want to hit. Process route is the location we're actually trying to hit this from. And the issue comes down to Uniswap v3 callback. Now, we can go find this code pretty easily. We can Google this, and with the name of this, it would be router processor 2. And we can find it. But I just copied it here for sanity. We can go to this location on Etherscan, and we can see all the transactions. But more importantly, we can find the code. So you can copy this code and analyze it locally. Now, I have my own development set up here, and I've already downloaded this code right here. So once I had the code locally, I wanted to figure out what the vulnerability was, but how do we actually hit this functionality? I decided that if I took some time to understand what the code does, had that functionality, that the vulnerability would probably be pretty apparent. So to start with, we are in the swap uni v3 functionality. You can either go source to sink or sink to source, where source is where the input comes from, and sink is the location in the code, or the kind of like the gadget or the ending location that you want to hit in the code. In this case, I find that going all the way back up from the sink is the easiest way to go. So we have the function swap uni v3, and this calls, this takes in our pool. What's this pool come from? Or where does it come from? It comes in from the stream parameter. So we're going to follow what that stream parameter is all the way up. We're going to search for Uniswap v3. There's only one place it's called. It's called in swap. Now we should document this just for our own sanity. We are going from uni v3 swap. That's where our entry point. So that's the place we want to end up at. And we have process routes we want to go. So we have some stuff in the middle that we need to now fill in. We have the swap function. And where is this called at? Probably not going to be the uni v2 pair that we care about. That's not the swap we actually want. This could be it, but we're not doing anything with Bento, so probably not it. Process one pool. Process is ERC20 token for cases when the token has only one output pool. That seems like a good option for us. We can go and try to find that. Cool. So this is within process route internal. So we see swap is called in swap. And this is called with process one pool. And that is in process route internal. Cool. Making progress. Now we are in process route internal, and process route internal is called by process route. And this is that route parameter we were talking about. Now we know how to actually hit that functionality. We should probably run all the way through our input. So the route is the actual input we want to use for this attack, because the route ends up controlling the input pool. Route gets turned into a stream, which we'll talk about what a stream actually is. Just consider it to be this ABI packed encoded blob of data. The first thing that the stream does is it takes out a value of 8 bytes. So it's reading a one byte or an 8-bit integer. And this needs to be 4 because we want to hit process one pool. The command code needs to be 4. That's where the command code comes from. So the first thing we get out of the stream is command code, and this needs to be 4, and it's uint8. Now, if we go into process one pool, it takes out an address, and this is the token that's going to use. Cool. So we have token. We don't know what we want this to be, or if it needs to be anything specific, and we have an address. Now we're going to call swap. And within swap, we're reading the pool type. And to hit the Uniswap v3 functionality, pool type must be 1. So pool type 1, and this is another uint8. Within the Uniswap v3 functionality, we are taking out a pool, which is reading an address. We're taking out a uint8 for a Boolean, and we are reading the address of recipient. So the pool is an address, but we don't know the value yet. We're taking out Boolean of some sorts. What was the name of that? 0 for 1. I actually don't know what this actually does within Uniswap. Don't know what that needs to be. And this is a Boolean / uint8 because those are actually stored exactly the same. And then we have the recipient. That's going to be another address. And we don't know what we want. Cool. So we know in order to hit this functionality, we need to call process route with a very particular route parameter. When we actually hit this, let's see if we can find the vulnerability. When we're making a call to Uniswap, particularly we have an interface with this, and it is calling the pool address with swap. Makes sense calling pool, or we're calling swap on a Uniswap v3 pool. But the magic lies here and here. You see, like I said before, the callback function, Uniswap needs to use the permissions of the contract in order to send funds to it itself. So Uniswap v3 callback is used in order to get the funds from Uniswap. And you can see that we are getting data, and within data is the token that Uniswap wants us to transfer and for what user. At the very end of this, we can see a call to safe transfer from that has. So what this allows it to do is Uniswap v3 doesn't have to actually have the permissions or the approval for this. Only this contract does. Because this contract has permissions to use this address and send data or send tokens from this user because the user approved it, they can then send it to message.sender, which in this case should be the Uniswap v3 pool. It's all pretty straightforward. It's just how Uniswap v3 works. What you're probably wondering is, oh my gosh, that's an amazing security issue because we can just directly call this and transfer any user funds to ourselves of any amount. That's awesome, but it's not that simple. The developer thought of this, and there is a check right here that makes sure that message.sender is same to last called pool. If you go back to Uniswap v3, where this is actually set at, you see that last called pool is equal to pool, and that pool is then called on. So this makes sure that only a trusted entity, in particular the Uniswap v3 pool, is able to call this back. But it has to be the exact pool address that we made on this call. Well, that's pretty cool. I like that, but is that going to work for us? The problem here is that the pool address is directly controlled by an attacker. There's no validation. This is, in fact, a valid Uniswap address. What this means is that we can call the Uniswap v3 pool on our own contract. Because we've called it with our own contract, and pool is set to last called pool, and we, in fact, control the pool, we can call the Uniswap v3 callback ourselves. By doing that, we can bypass this verification and use this to exploit the inherent trust that users have with this router. If the users approved more than they actually spent for this router, that means we can transfer their funds on their token to ourselves. The vulnerability is pretty straightforward, and I actually have a pretty good snippet on a blog post that I just wrote about this that shows us an even simpler light. We have two functions here, function 1 and function 2. Function 1 has an address called pool address that is being set. Function 2 then validates that the pool is equal to the message.sender. And because we called function 1, that is true. That is exactly what we hope for. Then we can do any sort of sensitive action like transfer the funds. This is a really watered down version of this vulnerability. Now we understand the vulnerability, we're going to exploit this inherent trust. But what's the actual plan for this? We can create a first, we need to call process route. In particular, we need to set the pool within the route parameter. Once we've done that, the pool that we're setting needs to have a swap function. This is so that when process route calls swap, as it should for a Uniswap v3 pool, we actually have that functionality there. Once we're inside of the swap function, we need to call the Uniswap v3 callback. And this can be used to abuse, or this is abusing the trust on the last called pool. Once there, we call the Uniswap v3 callback function. What we want to do is send a token of the user that they've allowed. We want to send the amount of funds, and we want to send in our victim. So that's a high-level overview of what we want to do for this attack, and we're going to write this proof of concept live. So we're going to start with a brand new contract. We're going to call it exploit live hustle. First, we need to start with a pragma first. I'm blanking right now. My recording is hard. Pragma solidity, thank you. And this can be 0.8. Usually that autofills. I don't know why I did it this time. That's okay. We're gonna call this exploit live. And we're gonna start with writing this contract with some magic values. The first thing we need to know is the router. And this is the Sushiswap router that we were looking at before. So we can address router equals this. And this is the Sushiswap route processor 2. We then need a token that we can exploit and a victim. In this case, we're going to use the user Sifu because that's where this was first launched on. And the address of Sifu is going to be our victim, and that's this. So 0x Sifu address. And the token that was stolen from Sifu was wrapped ETH. So we're going to then set the token here. And you can find these values dynamically. I just searched for the Sifu address. I looked through some of the transactions on Etherscan. And then for the token, you just look at the event logs to see what token was exploited. So with those set up, we can call the attack function. Within this attack function, we need to call process route, but we don't have anything actually defined to do this. So we're going to create an interface that we can then use in order to call process route. So I'm going to say interface Sushiswap router like, and then I'm going to go back to processor route and copy in the function that we want to call. We're going to copy in this function. We're going to need to remove that and remove that. Great. So now we can instantiate an object here. I'm going to say sushi router like sushi router equals Sushiswap router like router. And now we have, we can make calls to the sushi router using this interface we've set up. The only function that we want to call right now is this process route. If we go back, we can see what we actually need to provide for this. And if you read this code carefully, we can find out that a lot of it's garbage. We're going to look at process route internal, which just has the same parameters. And it takes in the token in, and it does a balance check here. It does a balance check here for the balance in and balance out initial, and then is checking later down here, has some sanity checks. Well, we just need a valid token here. But you see in this inline if statement, if the token in is native address, it just does address of this dot balance. Now this native address is meant to act as ETH that we've set to it. So we can do native address. You just copy this in there and use that instead. And this makes our exploit a little more gas efficient, I guess. But it makes it a little bit easier to follow. So for the token in and token out, we can just set native address. The amount in is the amount of tokens that we're initially going to pass in, but we can actually set this as 0. There's no sanity check to make sure it's greater than that. And the amount out minimum is the amount of tokens that should be transferred out at an absolute minimum because of slippage. So we can also set that to 0 because we don't care about that. And the 2 is really not used for our exploit. So we can literally just say 0. And the route is the only thing we actually haven't set. So route is going to be write memory route. This is going to be ABI coded. Now, if we look at what we had here, we already talked about what values you need to hit this. The first thing is an 8-bit integer, so 1 byte. And in this command code is going to be 4, so uint 8, 4. We have an address after that, and that address ends up not being used for our exploit, so we can just set it to 0. And then we go back to here, and we have a pool type which is of 1, uint 8 again. So we're going to write uint 8, 1. Then we have an address, and this is actually the key to this exploit here. If we go back to univ3, this function, this is where this pool is going to come from. And this is where we actually make the call. In order to make our exploit easier and not have multiple contracts set up, we're going to set up one contract and set up swap here. We're going to fill that out in a minute, but we want the pool to be this. So we're setting the address of this to be the pool address. Now we have 0 for 1 in recipient, and because both of these get used in the call, where we don't really care, normally this would be sent to the actual Uniswap v3 pool, but it's being sent to ourselves, so we can ignore that. uint 8 is the same as a bool, so I'm just going to set that to be 0. And then we can do the address of 0 again, because again, we're not going to use it. So at this point, we've created a proper route, but we need to implement this swap function. If you go to the route processor itself, it actually has a interface for Uniswap v3 pool. So we can just copy this in for our contract. Great. Now, when we call process route, we'll actually hit a callback on this. But just to make sure, we're going to do console.log because we're using hardhat. We can do that. We say hit swap function. Great. That's pretty rad. I need to import that still, and I can't have to do that off the top of my head. It's something like this. So we've imported hardhat console, so that should go away. And now we can use yarn hardhat compile on this. And in a few seconds, I should compile code. Cool, we don't have any bugs in it. That's awesome. So in this tab, we have the code we're going to execute. And in this tab, we have a Uniswap v3 node that is, sorry, not Uniswap v3 node. We have a node that's run locally. And I forked this right before the exploits took place. Now we're going to do yarn hardhat run, and we need to set up a script in order to do this. So I made the script earlier just because it's easier to do it that way. But it's a pretty standard hardhat deploy contract and execute. We're getting our exploit live contract. We're calling deploy. We're calling deployed, making sure that this actually did deploy. Then we are calling the attack function on this contract, and then we're waiting. So pretty straightforward. So it's going to be scripts and hack sushi live. Oh, I actually messed that up. I need to specify the network for this too. Otherwise, it will run locally and that won't work. Let's deploy our contract, and it launched it, and it reverted. Well, dang it. What does it say? Unknown command code. Oh, I know why that happened. If we go back to our contract here, exploit live, you'll notice that this is using encode. And there are actually two different ABI encoding functions. There's one that takes all of the static sizes and places them into 32 bytes, which means that a UINT8 would actually be 32 bytes instead of 1 byte like it could. If you use encoding packed, it will set it, this 4 will now be 1 byte exactly, instead of being 32 bytes. This threw me off initially when I actually ran this code, but if we look at the stream processing, it's written in assembler, and I was a little terrified of this at first, but if we look at it, there's a pretty good giveaway. We see read UINT8 and read UINT16. And the only differences between these are 1 and 2. Because of these slight differences, it made me think that this was likely processing data in the packed format. It was going to take out 1 byte and return that, versus read UINT16 was going to take out 2 bytes. So this is putting an 8-bit integer, 1 byte, and taking out 1 byte, which indicates that this is likely using the packed format instead. So now that we've saved this and we've used encoding packed, this should work again. So it's got compiler code. Now it should try to deploy our contract. And this gave us another error. Do we do something wrong? Not really. If we go back to the contract, we can see that this is an error message from the router itself. See, route processor Uniswap v3 unexpected. When does this occur? It occurs directly after our call to swap within Uniswap v3. This is used in order to confirm that the callback was actually made. So it sets in. It's saying that last called pool should be set to impossible pool address. If we go back to Uniswap v3 callback, we can see that's exactly what this function does. In our exploit code, we haven't called the Uniswap v3 callback yet. We've just called swap. Are we sure we actually called swap though? And yes, we are. You can look at the console.log from the node that we ran, that we can see our console.log, which is pretty rad. So we were able to successfully call swap on our own contract from the context of process route. That's awesome. At this point, we need to implement the Uniswap v3 callback function. And we can do the same thing we did before. We can go and grab this callback from here and just add it to our contract interface that we've set up. So we go here and we can add this to our interface. Perfect. And now we can call this function once again. So this is create a router. And on our router, we want to call the call views. What's wrong with this? You specify the visibility. So Uniswap v3 callback, and this takes in 3 parameters that we care about: the deltas, amount delta 0, amount delta 1, and the data. And we can go read the code for this. So amount delta 0 and amount delta 1 are only used on this single line. This is saying amount delta 0, if it's greater than 0, then use amount delta 0. Otherwise, use amount delta 1. I don't know too much about how this callback actually works, but it looks like it's intended to use amount delta 0 if it's positive, and use amount delta 1 if it's positive. So in practice, all we have to do is set amount delta 0 to be the amount we actually want to steal. And then this amount is used in the safe transfer from call. Cool. So for the amount 1 delta, I'm going to set it to 0. And then we need an amount, which we will need to calculate. And then we also need the data. I'll create these up here. 256 amount 0, and we're going to do bytes data 2 equals bytes memory data 2 equals ABI.code. In this case, we actually want ABI encode instead of ABI encode act because this is using ABI decode, not decode. So how do we actually calculate the amount of funds we want to steal? And it turns out that this comes directly back to the ERC20 standard. We want to see the amount of funds that this contract, the router processor 2, is allowed to spend, because we're abusing that trust in order to steal the funds. So in order to calculate this, we're going to calculate two values. First, we're going to calculate the balance, and then we're going to calculate the allowance. I believe that that this contract is actually going to be using the OpenStack ERC20. So we can actually use that ourselves in here. Great. And this will allow us to use the ERC20 interface. And remember how we set the token for exploitation before? We can now set that to be here. And we can call balance of on our victim. And this will get amount of token for our victim. And similarly, we're going to call ERC20 token, and we're going to call allowance. And this allowance call is going to say we're going to check the allowance that victim is allowing this router to spend. So we're going to then put in router there. Amount of token that the router can spend of victim. In order to calculate the amount, we want to take the minimum of these, because if they have a very high allowance but a lesser balance, then if we try to send the allowance, they're not going to have enough funds to send, and it will revert. If we do it the other way, though, where we try to send more balance than they're allowed to send, then we'll also get a revert because we've broken that part of the user. So I'm going to say balance is greater than allowance. Then we're going to use allowance. Otherwise, we're going to use the balance for this call. Cool. So now we know how many funds, amount of funds to steal. Cool. So we've calculated that, but we still have one more parameter to fill out. We have data too. Within route processor, the data parameter has two values encoded. It has token in and from. Token in is the token we want to steal from, in this case, wrapped ETH, and from is the user we want to steal from, aka victim. So we can use token in and victim for this call. Cool. The one mistake I made is that we need to convert this to int256, because that is what this actually takes in, and that would have been a unit. Need to put a comma there, and hopefully that works. Before we actually run this exploit, though, I wanted to show you guys the user. I have some Etherscan tools that I've written, or Etherscan, EtherRPC, and that sort of thing. And in this, if we look at for address, this is calling our local node that's running, is checking for our users, so Sifu, balance of wrapped ETH. So here we're creating a contract with our coin address, which is again wrapped ETH, and then we are going to check the balance of our user. And then we were checking for the allowance that the user is allowed to send off to a particular router. Sorry, we're using the user address for allowance and seeing how much funds does this user allow this other user to use, in this case, the router. So if we hit balance for address, it will show us the balance and allowance. This is about $3-ish million worth of ETH, And this is essentially an unlimited allowance. So in this case, we can only transfer this much ETH, which is still 1,616 ETH is still a lot. If we go back and run our exploit again, we can see if this runs. And there is a non-zero chance that I have some bugs in my code, or I had some really subtle flaws that we need to fix in a moment. Cool. So what's the first flaw? First flaw is amount. I am not setting that to the right type. We'll try that again. Cool. Looks like it compiled successfully. Now we can see if this call succeeded. Let's try to launch the attack. And the attack worked. Great. Now, if we run this script once again, we can see the balance has changed. The balance of this user is now 0, and the allowance has gone down a little bit. It's hard to tell, but you can see that some of these numbers have changed. Where has it changed? Changing here somewhere. Yeah. So that's pretty awesome. We just stolen $3 million worth of ETH in this relatively simple bug. To recap, within process router, there is a vulnerability that allows us to set the pool. And this pool is a very trusted entity. Once we control that pool, we can then have it call our own swap function. And because of that trusted aspect of this call, we are able to make a call to Uniswap v3 callback, which allows us to spend arbitrary funds for arbitrary users that have approved this contract. This is a classic confused deputy problem, if you've ever heard that. But what if I told you we can make this much worse? We can do so much better. See, we only stole it from this one user. How would we actually go about stealing this from all of the users? The easy way to go about this would be going to here on Etherscan and looking at all of the transactions. If we look at all the transactions and imagine that this was in the past prior to this exploit, we could have checked to see which users were actually approving this. So we have a execution here, and on this call to the Sushiswap contract, this user would have had to have approved this contract to send funds, and that is a pretty big difference. It's a pretty easy way to analyze what users we can exploit. So we're going to click on this user, and within the receipt of a transaction are the logs. We can see that there is a from, there is a to, and there is a value. Within this, we can actually check to see what was used here. We can check to see this user had to approve funds to be transferred by this contract. We can see what token they allowed and the amount they sent. Using this information, we can script looking at all of the transactions that this Sushiswap router has used and find a list of vulnerable users with their vulnerable token. Now, one way you could go about this is look at popular tokens and look for events on the approve function, but I found this to be much easier and a lot more direct. All these users are likely to be vulnerable unless they only approve what they were required to. So this one, unfortunately, I can't write live. I'm not that cool. So we are going to look at some code I already wrote in order to do this. The first thing that I'm doing here is I am calling the Etherscan API. I would show you this, but I don't want to give up my API key. So we are calling list transactions for the Uniswap v3 router to Etherscan, and we're sending it off. Once we send that off, we are removing the first entry because it will be the contract creation, and I didn't want to do that. I didn't want that transaction. After that, we are setting this to be our local node once again. We are importing the ERC20 API for future calls. Now, here's where things get a little bit tricky. We're going to make calls directly to get transaction receipt. And in order to make this call, we need the transactions. I didn't know of an easy way to get the transactions associated with a particular address, but Etherscan has that indexed for us. So I used that and then told it to get the address of all transactions. Once we have the address, get all the transaction receipts. Once we have all the receipts, we can then get the logs, which has all the event data inside of it. Once we're looking at all the events, we want to identify the transfer event, because that is the transfer from call that that we want to look at. In particular, we want to find all transactions that have the from of this to be the from of the transaction. So who sent this transaction initially to the from of the event. This allows us to find all the users that called this directly who are vulnerable to this attack. We can do this by looking at the token address, the from address, and the to address of a particular event. With this, we append this to a list. We append the token address. So this, in our original exploit, this was the wrapped ETH, and then this was the Sufer user. But because we want to find all users, we need to do this dynamically. Once we have a list of users and tokens that are potentially exploitable, we want to find the amount of exploitation that's possible, or if they're exploitable at all. So this this function is iterating over that list we just made right here of all the users. And it is going to create an ERC20 contract for that particular token. It is then calling balance of for that user, and then allowance for the user and the sushi router, because we're abusing this trust. If both of these are greater than 0, it means that there are some funds that we can steal. Once we run this and there are funds to steal, it will append to our exploit data, and this will output to a JSON file, which we will iterate over in a little bit, but it also prints out the token, the user, the balance, the allowance for MC. So to recap, this script is going over a list of transactions from the sushi router. Once it's done doing that, it will get the transaction receipt for all the transactions from the sushi router. From the transaction receipt, we're going to look over all of the events. Within those events, we're going to look for the transfer event. And we can then find the token and the user that were vulnerable to the attack because of that. Then we can find out how much we can actually steal from that user once we know that information. Great. Before we actually iterate over this, though, we're going to modify our contract slightly to be a little bit more robust. And we actually need to reset our node because we stole some funds from it. For the attacker contract, we now don't just want a single victim and a single token. So we're going to set that ourselves. We're going to do address of token and address of victim. And we're going to set these dynamically now. So we're going to set token to be underscore token, which will provide in our script. And we're going to set victim to be underscore victim. Okay. So this is setting exploit settings. Now, when we call swap, it will use the proper victim and the proper token for this exploit. What does the script actually look like in action? You get logs for address. And if this is now set up correctly, you can see that it's actually calling get transaction receipt there a bunch of times. I just don't have any login for this. But eventually this will stop or start appearing with the values that we want to see, particularly the vulnerable users. There we go. So you can see tether USD. There is a user with this amount of balance to this allowance, which means we can only take this much funds. We have Uniswap, and we can take a lot of funds from this one. We have a bunch of tether. This is about $38,000, if I recall. Sorry. 360, maybe. Wait, we have 6. This is a 6 decimal coin. So yeah, $3,800. But this wrapped ether user is still the most by far, the CFU user. But now we have a pretty good sized list of users that we know are exploitable, which is freaking awesome. So if we were going to perform this white hat hack in retrospect, this is what we could do. Or if you're a bad guy and actually want to exploit this, which shame on you, don't do that. This is also what we could have done. Now, like I said, there's probably a better way you could have done this. You may have been able to look for popular tokens who approve this because that also has an event. But I found this to be the easiest and most efficient way to do it. So now when you go back to our Sushiswap live contract, and we need to rewrite this code. We're going to read from a file. So we are going to use this require statement here. And once we're in that require statement, we can now we can now read from a file. And we're going to iterate over each one of these users. Now, this is where this is outputted to. And we're going to iterate over all these users. For I equals 0, I less than users dot length, I plus plus. And this attack launching code is something we actually want to put within this loop because we want to run this over and over again. I'll put a little thing here, make sure it's. And now we need to get all of the users for that, or all the information from the users. So we want the victim address. If we look at our file here, we can see that it's outputting victim address, the token name for readability, victim token address, the victim balance, the victim allowance. So we'll log all that stuff just so we can see it. Context victim, this is going to be users of I. And we're going to get the victim address. So we actually need to repeat this a few more times. We're going to do victim token. We're going to do token name. Victim balance. And victim allowance. Now we have all these values. Just to see this attack in action, we're going to print this out. And we can do some fun string interpolation with this. So we're going to do console.log. And what do we want to see? We want to see the victim address. And great. We want to see the token name. And we probably want to see the amount of funds we can actually steal. So we can do the same logic. So amount to steal equals. This is going to be we did the same logic as before. Victim balance, allowance. If its victim balance is greater, then use the allowance. If the allowance is greater, then use the balance. We always want to use the smaller of these two. So the amount to steal can then go here. Great. Now we can call this. We need to go back to our contract and see what we were using for this call. I can't remember which ordering we use. So it's token, then victim. So victim token and then victim attributes. Cool. Just clarify it's token victim. But I still think we have one other thing we want to do here. I want to see the victim balance afterwards. So just to make sure we're stealing the right amount, we are stealing some funds. In fact, I'm just gonna put this at the beginning just so it's even easier to see for us. Now we're getting the IERC20 contract at the victim token address. This is what we're doing here. And then we can call, to get the new balance, we can do amount after equals await. We can call token contract. I can type balance of, and this is going to be the victim address. And if we output that, amount left, and use amount after, we should see that coming. So hopefully I didn't mess up anything, but that is highly unlikely. So we reset this. We are now iterating over a list of users that we ran a script to find. We are going to specify a token, the token and the user that we want to exploit using this. And everything else is exactly the same as before. We created this loop with the users and we made this call dynamic. So if you call this one more time, we can start iterating through all of the users. Assuming that my JavaScript works properly, which there's a good chance it doesn't. It actually worked. Nice. So we can see here that there's amount of funds we get to steal, but we don't have the balance there. That's my bad. So, but with this, you can see the amount of funds to steal, and now they have 0 left in their bank account. We stole all of their funds in that case. We stole a good amount of funds in this case. We stole all of their funds, Anything time you see amount left 0, we stole all of the funds. And this is a pretty horrific exploit when you think about that now and what this actually could have, or what this could have been in this context. This is our Sifu user who we just stole about 1,600 ETH from. So cool. That is the exploits, and this can keep running. If you're going to do this in the real world and do a white hat hack this way, you would probably want to use something like Flashbots or obfuscate your contract in some way. But as Trust pointed out in his tweets, the dark forest is real, man. It really is. Like you got to think it's 10 times more powerful than you probably think it is, because as soon as something's up, it's going to get. As soon as something goes public, everyone and their mom is going to start exploiting this to steal money. It's really unfortunate. From the live recording, I had some questions that might be worth going through. Not from the live recording. Yeah, from the live recording that we're not going to post. The first one was, what was the hardest part for me about this? And I think the hardest part for me was actually scripting the Etherscan and ETHRPC. I'd never done that before, but I found the documentation for Etherscan and ETHRPC to actually be pretty good. So I think it was just a matter of how to use those APIs correctly and get the data back and then parsing it. But it was also hard because I don't know what data is where. It took me some time to figure out that the events would only be in the transaction or the receipt of a given transaction. The other hard part was just understand the vulnerability. I felt like once I understood this, it felt pretty straightforward, but not being the most familiar with Uniswap v3 protocol, it was a little bit to grasp. But after I did some reading, everything made sense to me. So cool. That's what I got for you guys. This is within the Open Sense Discord channel. It's really awesome. I've jumped on calls a few times with people asking questions, and it was amazing how responsive and awesome people were about stuff. So join that. Follow my blog. I write random stuff all the time. I have blog posts about blockchain security things, but also I had to scoreboard last year. That was pretty fun. I have a resources page that I document all my notes on. So recently I've been reading, there was an article released about different proxies. I wrote some notes on that, learned about the Yearn finance hack. So I have a lot of notes here as well. My Twitter is @Dooflin5. I think this should. do fun 5. Hacker handle Strikeout. Yeah. Feel free to reach out if you need anything. Thanks for the Open Science community for this opportunity to do this.